Hello everyone. We're going to be starting on chapter 2, which is called Change Over Time, which that is also evolution, means change over time. In our last chapter, we tried to work on some science skills and trying to look at humans like a scientist would, and we worked on writing testable questions, scientific method, and observing. And we'll continue our work on science skills. We'll also do a lot of work with using models in this chapter. All right, scientists use models to help explain the world around us. We'll look at fossils and a very important fossil named Lucy, who was discovered the year I was born. We'll learn how evolution is like a big, huge puzzle with tons of pieces, and some of those pieces are not even found yet. Don't you love putting a puzzle together and having pieces missing? It's like a big mystery. We'll look at what a theory means. We've already defined what a hypothesis is, but we'll look at what theories mean, and we'll look at some of the important components of evolution and how we know what we know. We'll really also focus on evidence in this chapter. Well, evolution is a theory, so I want you to think, all right, in other classes, anything, what other scientific theories do you know of? You can stop the video right now and jot a few of them down. By the way, you should be taking notes. When you take notes, always have a title, like you see in my slides here, a source, where is this coming from, like a page number, or just the fact that it is notes, and then a date. All of those things are important so that you can go back later and remember what you were doing, where you were doing it, and where you got it from. All right? So what important theories have you heard of? Because the word theory is kind of thrown around in everyday language. And in everyday language, it really doesn't mean much. It's actually more like a guess. But in science, theories are absolutely, tremendously important. So what theories do you know of? Well, some that I usually get when I'm in class and I have students tell me what theories they remember. Usually evolution theory comes up. Big Bang theory is often mentioned. Germ theory, cell theory, I like those two because those are biology-related theories, cell theory and germ theory. Atomic theory is another one, continental drift theory. All of those are theories, and those are extremely important ones. So what is a theory? Well, we know a hypothesis is an educated prediction that you should be able to test. A scientific theory is much more than that. Move myself out of the way there. So a scientific theory is a comprehensive, that means there's a lot to it, a comprehensive explanation for a set of natural phenomena. So basically it's explaining something huge that's going on in nature. And it's not just one little sentence to describe it. There's a huge amount of stuff to describe it. And not just one scientist can contribute to this. Like, for instance, in evolution, you may have heard of Charles Darwin, and they may say Darwin's theory of evolution, but really it's not just his. He just has one little part of it that he helped explain. But it's many scientists contribute to theories over time. And then it ends up having tons of supporting evidence that you keep building upon by having many tested hypotheses over time. You can actually say that these theories stand the test of time. There's so much evidence supporting them. And the cool thing that I love about science, what I call the nature of science, is that even though there's all this all of this evidence to explain a theory, that it still has this openness to change, that you leave that little window open, like I've talked about before, this openness to change. Because look at us as humans, our big brains, we're always thinking of new ways to do things. We're making new technology, and new technology can lead to new discoveries. So in a scientific theory, it's open to that change as new discoveries are made. Now, usually with a theory, when new things are discovered, usually it's not enough that it's going to change the whole theory. Usually it's just tweaking little parts of it, like fine-tuning it so that we know even more than we did before. An important thing with a theory is that we look at the evidence and what the evidence tells us. It's not like a belief or anything, something that we want to be true. We look at what the evidence tells us, whether we like it or not. Like right now, what the evidence is telling us on the coronavirus. We may not like it, but we have to look at what the evidence tells us. So think about some of those important theories, like germ theory. Germ theory, basically, that germs, bacteria and viruses and other pathogens cause disease. I mean, have you ever questioned that? I'm guessing not. There was a time when it was questioned, and they used to think supernatural forces caused diseases, sicknesses, but with the help of the discovery of the microscope and testing hypotheses, we helped to quelch that. But that is so important. It actually just tells you that we're so sure of it that nobody questions the fact that germs can cause disease. Not all germs do, but they can cause disease. We don't question that. That's how we're so sure. There's so much evidence that supports it. But we can still learn more. We leave that little window open to learn more all the time. The same thing with cells. Have you ever questioned that cells exist? Cell theory. And we can look under a microscope and we can actually see cells. We see them. They're right there. So why are cells just a theory? Well, there you go. You shouldn't say just a theory, because in science, theories are so important. They explain what's going on in the world. There's so much evidence. So it's the same thing with the theory of evolution, that there's so much evidence supporting that as well. All right, so why is evolution a theory? Well, like I said, there's an enormous amount of evidence, and then all of that evidence supports it, not just some of it, but the whole theory as a whole. And it comes from many different areas of science, not just biologists, but other scientists as well can contribute evidence. And we can even use, and this goes for all theories, that we can use theories to create new hypotheses and new predictions to predict new phenomena. That's kind of cool. And it's almost universally accepted by scientists around the world. All right. So what about scientific laws? These are also different. When you hear of a social law, social laws are not the same thing as scientific laws. Scientific laws are very specific. Unlike a theory is more of a broad base of knowledge, but laws are very specific, and they describe relationships between things in the natural world. So these laws are not broken, and some of them even become part of scientific theories. All right, so what I would like you to do to get more information on this is to read that article on page 135, Just a Theory. One thing that I like about our textbook is that it reads a lot like a scientific article. So when you read those little blurbs in there, it's a little more interesting than reading a textbook. So it doesn't take too long either. They're pretty short. So read that and get some examples for just a theory. All right. And then be able to define what a hypothesis is, what is a theory, how is it important, and then what is a scientific law. All right, now I've jumped over to our textbook to page 88. That's our textbook, page 88. One of the first parts is a part called Lucy, again on page 88. Populations of living things on Earth change over time. Scientists use evidence and logical inference to reconstruct these past events. For example, since the mid-1800s, scientists have been piecing together the long line of species and populations from which modern humans emerged. This long line of ancestors is called a lineage. Some of the most important pieces of this complex puzzle are the fossilized skeletal remains of individual hominids that lived millions of years ago. All right, hominids are erect walking primates that include modern humans and extinct human-like species. All right, so in our last chapter we learned what a primate was. So in classifying humans, of course, just to give you a little review, our kingdom is animal. That's why we call ourselves the human animal. Our phylum, it's called Chordata. I don't expect you to know that quite yet, but it basically means we have a backbone or had a backbone sometime in our lives. And that's a big, huge amount of organisms that we share that in common with. All right, so we go kingdom, phylum, and then class is mammals, meaning we have warm blood and fur and all that good stuff. And you know there's a lot of mammals in the world. After class comes order, and our order is primate. All right, so we now know what the other primates are. Monkeys and great apes and humans are all primates. Well, after order comes family. And our family is hominids. So unlike those other areas of classification, right now we are the only hominid on Earth, at least that we know of, unless somebody maybe discovers that the Yeti or Sasquatch are really around these days. But as of what we know right now, we are the only hominids on Earth at this time. So we're kind of alone in our family. So hominids, again, are erect, walking primates. And it's the modern human. So what other hominids have there been? Well, you've probably heard of cavemen before, which the real proper term for them is Neanderthals, or Neanderthals is what they're calling them now. They went extinct about 35,000 to 40,000 years ago. So they would have been some of the last hominids that were on Earth, but for some reason they went extinct. And yes, according to the fossil record and what the evidence tells us, that humans, as we know them now, modern humans and Neanderthals, were around at the same time. So there was a time on Earth where a human could have looked eye to eye with a Neanderthal. What a moment that would have been. I would have liked to have been a fly on the wall to see what would have happened. But well, dated at this is not a Neanderthal. Lucy is not a Neanderthal. She's a different she's a hominid actually, but a different genus. So after family comes the genus and species. So humans are Homo sapiens. That's our genus and species. And Lucy is actually Australopithecus afarensis. So that's kind of a mouthful. So Lucy, although she's a hominid that's extinct, would have been a different genus and species. So doesn't even share the same genus with us. But Neanderthals probably would have shared our same genus and would have been Homo neanderthalensis. All right, so this Lucy character here is dated at about 3.2 million years old. Now that's old. So the skeleton shown in the opening photo is one of the oldest and most complete hominid fossils, and we continue finding more, but she would have been the first of her species found back in 1974. That was a good year. Someone kind of important was born back then. So scientists named the skeleton Lucy because of a popular song that was by the Beatles at the time. All right. So how do populations change over time? And so that's what we're going to start exploring by taking a look at this Lucy fossil. And so if I'm looking in the book, I'd have to back up. There it is right there. There's the Lucy fossil right at the beginning of chapter 2. Or you can go into my video there. I had it shown a little bit earlier. Or go into the book. So that's the Lucy, and that's what scientists would have had to go by. So read that scenario, Digging Up the Past. It's right here, starting on page 89. Interesting, again, little story. It reads more like a magazine article than a textbook, and it really is very short. It's just that page there. And then here's what you need to do in your notebook. And you need to have this ready to show me at our next class meeting. Read Digging Up the Past. It'll give you the story of Lucy, and it's going to give you some details to do what you've got to do here. So then, number 2, describe in your science notebook how Lucy might have looked. Use words and sketches to convey your ideas. All right, do I expect it to be a work of art? Absolutely not. But do a sketch based on what the fossil looks like in the picture and what the story tells you. It's going to give you some information. Do a sketch and some descriptive words of what Lucy would have looked like. Since we've been talking about humans having opposable thumbs and being bipedal walkers, pay attention to how you draw Lucy's hands and feet, because it did say that she's a hominid and hominids walk upright. Number 3, describe three things Lucy might have done during a typical day and how she'd go about doing them. So how are you going to know that? Well, you're going to have to do what scientists do. Go with other primates and how we look at their behavior. What do other primates like chimpanzees, other apes do? What do humans do? So describe 3 things she might have done on a typical day. So we're going to make some inferences there that since Lucy was a hominid, then her behaviors would probably be similar then to other hominids and other primates. That's called an inference. It's based on evidence. You're not just guessing, you're basing this on evidence. Number 4, make a T-table in your science notebook with 2 columns. Label it evidence and inference. Then fill in your T-table based on what you read in Digging Up the Past and what you read here. Though Lucy's complete skeleton was not recovered, scientists are still able to infer many things about her. For example, the structure of Lucy's pelvis and the bones that make up the hips. It was carefully documented and measured and all that. Her pelvis was compared with that of modern chimps, apes, and humans. Plus, we've now found more of these Lucy fossils, Australopithecus afarensis. Humans walk upright. Scientists call this bipedal. Apes and chimps are knuckle walkers and are not bipedal. Lucy's pelvis shared many features and with the pelvis of modern-day humans. From the evidence of Lucy's fossilized pelvis and the pelvis of modern humans, scientists made the inference that Lucy walked upright. Evidence from Lucy's knee bone also supports the inference. Scientists agree that hominids, apes, and chimps came from one species that existed in the past. This extinct species is called the common ancestor to all 3 species. Recent estimates suggest the ancestral species lived about 7.3 million years ago. Chimps, apes, and all other primates are not exclusively bipedal. Based on this evidence, scientists infer that the common ancestor of apes, chimps, and hominids was not bipedal. What does that mean about Lucy? In the lineage from the most recent common ancestor of apes, chimps and hominids, which existed about 7.2 million years ago, to Lucy, who existed at 3.2 million years ago, there was a change from not being bipedal to being bipedal. At one time, it was thought that Lucy was like what you call the missing link between other primates and humans, but since then we've found other different fossils that would indicate that there were others. All right. So do number 5. You do not have to do number 6. Then do the analysis. Number 1, A and B, and then number 2. All right, not too tough. Again, everything here except number 6. You do not have to do number 6. And you're working on Lucy, pages 88 to 90. So the next time I see you, you should have some notes on what a theory is, and you should have this part on Lucy done. All right, plus the analysis here at the end. 1A and B and 2A through C. Again, drop me a line if you have any questions.